Good morning, everyone. It's a great pleasure to have the Swan visiting professor this year. I know everybody knows a little bit about Henry Swan, but I thought I'd give people who didn't know his history a little bit of the history of the Swan lectureship. Henry Swan was the first full-time chair of the Department of Surgery. Prior to when he became chair, all of the chairs of surgery had really been a part-time job because Colorado General Hospital at the time was a public safety net hospital, and the people who staffed the Department of Surgery were all basically volunteer surgeons. But he became the first full-time chair of the Department of Surgery in 1950, and he stayed the chair of surgery up until 1961. He was a native of, he was a native of Denver, and he had been born in 1913. He went to Philip Exeter Academy, and then he went to Williams College back in Massachusetts before he attended Harvard Medical School and graduated in the class of 1939. One of his classmates and best friends was Franny D. Moore, who many of you know was kind of the father of surgical metabolism nutrition. He did a pathology residency first at Colorado General Hospital. And if you don't know, Colorado General Hospital is now called University of Colorado Hospital. In fact, when I came to interview for residency here, I got in a cab and I asked them to go to University Hospital. And the cabbie said to me, "Do you mean CG?" And I said, "Well, I don't know what CG is, but I want to go to University Hospital." Anyway, he then did a surgery residency at the Peter Brent Brigham Hospital and also did training at Boston Children's Hospital and finished in 1943. And as most people who did any kind of surgical training in the early 1940s, he ended up in Europe in the 5th Surgical Group. He then returned to Colorado and became an assistant professor of surgery in 1946. And this is a pretty fast ascendance. He went from assistant professor in 1946 to chair of the department in 1950. His biggest interest was in hypothermic cardiac arrest and then doing very rapid surgical care in the heart in less than 10 minutes for things like valve repairs. And I put this paper up on the slide, which was a presentation of the first 100 cases of hypothermic cardiac arrest. And if you look at the bottom left of the manuscript page, what you're going to notice is that he presented this series at the American Surgical Association. The meeting was just this past Thursday, Friday, and Saturday. And if you look at the date on the date of his presentation, it was April 27th in 1955. So it seems a little bit coincidental that today we're doing the Swan visiting professorship. He retired from the University of Colorado in 1961, but he then went up to Fort Collins and was a professor of veterinary surgery in 1963, where he continued to do research on hypothermia, and he eventually published a book on thermoregulation as he was studying hibernation in various animals. And then he fully retired in 1982, passed away in 1996. The picture on the bottom right is of Dr. Swan and his wife, Jerry. They were mainstays at various department functions back when I was a resident. And Jerry continued to come to various department functions throughout her entire life. And with that, let me hand the podium over to Dr. Neidham, who will introduce our distinguished visiting professor.
Thank you, Robert. The Swan Lectureship honors individuals who have fundamentally advanced surgical science, clinical innovation, and the care of our patients. It's a privilege to introduce Dr. Markmann today. Dr. Markmann currently serves as the Vice Chair of Transplant in the Department of Surgery and Vice President of the Transplant Institute at the University of Pennsylvania. and he's currently the president of the American Society of Transplant Surgeons. He completed his undergraduate training at LaSalle University, followed by both his MD and his PhD in immunology at Penn, where he completed his general surgery residency before pursuing a fellowship out at UCLA with Dr. Busatil. He is internationally recognized for a career that has seamlessly bridged immunologic discovery and clinical transplantation. His work has advanced our understanding of immune tolerance while also contributing to progress in islet cell transplantation, stem cell derived therapies, and ex vivo perfusion. More recently, he's been a leader in xenotransplantation and using sophisticated preclinical models to address our ongoing challenge with organ scarcity. Prior to returning to Penn, Dr. Markmann spent a decade and a half leading the program at Mass General and Harvard Medical School. But more importantly, beyond these extraordinary academic and clinical achievements, Dr. Markmann is widely known for his character. He's a gentleman in every sense of the word. He is a meticulously technical surgeon and a deeply devoted father and husband. Those who have trained with him, Peter is one of them, consistently speak not only of his excellence, but of his integrity and his ability to be an amazing mentor. Please welcome Dr. Markmann.
Well, good morning, and thank you for the very generous introduction. It's a real pleasure to be here with the team and to speak with you about innovation and modernization and transplantation. It's an honor to be the 44th Henry Swan Visiting Professor, and in particular, it's an honor to be here with Dr. Keneally, who's been a long-term friend. So as the surgical field has evolved, transplant continues to offer big open cases, recent adoption of robotics, in addition to what is likely the most science and innovation-oriented surgical divisions. So it's an exciting time for transplant, though currently mixed with some difficulties around the government's efforts to modernize transplant that we'll discuss briefly. The photo here shows a nice juxtaposition of the old museum at Penn from 1887 with the new modern hospital that sits in the background. These are my disclosures. I did a bit of reading about Dr. Swan. Of course, he was a member of a unique generation of surgeons who had to develop his field from scratch with ingenuity and perseverance, and it must have been an amazing time. And I'll expand on this phenotype a bit with you this morning as it's become even more relevant today. I'll start at the beginning. So Joe Murray's successful kidney transplant was a monumental step for the field, but perhaps equally important was the science that supported the field's advance through basic investigations from individuals like Sir Peter Medawar and others. I also find it of interest that the Nobel Prize for Medawar was awarded some 30 years before it was awarded for Murray. So I'd like to capture some of transplant story history with three eras. These are a bit arbitrary that I've laid out, but think it still illustrates some interesting points. So the leap to a successful kidney transplant by Murray was followed a decade later by the first pancreas and then the first liver by Starzl, heart and lungs that followed. But what really drove them to success, like Dr. Swan, was the desperate need for progress, bringing new ideas and tools to advance the care of their patients. There was no playbook. These were true pioneers of the field who had to design and invent from scratch. Things like organ preservation and immunosuppression and surgical technique were, of course, critical advances. And I suspect that perhaps the lack of stringent oversight may have also facilitated success. To my view, that period that followed, that I've dubbed the Dark Ages, lacked the same level of noteworthy advances in innovation, but instead was more focused on growth and refinement of technique. And this lasted till around 2015. There were a few key exceptions. in the dark ages, including eradication of hep C for liver patients and the development of organ swaps and chains that have been very fruitful at making more organs available. However, what has happened or is happening in the third era has been truly remarkable, and I'll focus the second half of the talk to speak of some of these key developments. So the period in the early 80s was romantically called the liver wars. During this time, there was little or no regulation or oversight for the field, allowing fierce competition between centers who individually managed all aspects of donation and transplant for their patients. And by the way, the picture of liver wars was produced by AI and did a pretty good job, I think. So there were examples of hospitals with a candidate donor and no recipient to receive the organ, or a recipient in need but no access to a donor. There were also stories of two separate teams rushing to a hospital to recover organs, generally for a liver, with the team getting there first, getting the organs. Not surprisingly, the lack of oversight and regulation led to disparities in access and wasted organs. In addition to the general disarray of the time, a second force that pushed the field toward regulation was a Virginia physician named Barry Jacobs. He recognized that the chaos of the day was not working, and instead, in 1983, he proposed a plan to start what was called the International Kidney Exchange to commercialize kidney transplants. He proposed to charge a fee of a few $1,000s to connect patients with end-stage renal disease to potential donors. And these donors were often from underserved areas. So Jacobs' proposal, though never realized, plays a pivotal role in shaping US transplant policy and ethics, advancing the development of the OPTN. And his actions are often cited in discussions of commercialization of organ donation and the legal frameworks that govern transplant today. So the National Organ Transplant of 1984 worked to address these issues. And the key provisions were creation of the Organ Procurement and Transplant Network, a national system to coordinate allocation and equitable distribution, establishment of the Scientific Registry of Transplant Recipients, or the SRTR, for data collection and analysis. It also prohibited organ sales, and again, perhaps that was partially due to Dr. Jacobs' efforts. It also funded the organ procurement organizations that we'll talk about a bit more in a little while. Federal oversight was through HHS and HRSA to oversee the Organ Procurement and Transplant Network. In 2000, the final rule was placed, and it sets out how the US organ allocation and transplant system must operate. The issues are what might be expected: equity and allocation, transparency and accountability. But really what was going on at the time were issues of geography. There was a case that stood out where there was a patient in New Jersey who needed a lung transplant, and lungs were available across the river in New York, but couldn't be accessed because of these artificial boundaries that prevented broader sharing. So in 2023, the government worked to modernize the OPTN with the Secure the OPTN Act. This was passed into law in 2023. It allowed for more spending on transplant, which was a very positive outcome. But it also looked at the current contractor, UNOS. So there was a relationship between UNOS and OPTN. And for years, it seemed like OPTN, UNOS were synonymous. But to be clear, the OPTN was the governing body that set policy for the network, and UNOS was the first contractor in 1984 hired to support the OPTN work. So UNOS won the first contract from the OPTN in 1984 when the network was put in place. And then every 5 years thereafter, the contract was opened for a bidding process. And every 5 years for 40 years, UNOS was awarded the contract. So where things went awry was that over time, the boards of UNOS and OPTN had the same members. This was obviously a structure that was ripe for trouble and conflicts. HRSA recognized this, and with modernization came full separation of these entities, in which the boards were disentangled and UNOS was broken into a number of different contractors. And this is part of the process that's going on now that has disrupted the system. This shows signing of the bill in September of 23. On a positive note, it did add significant funds to the effort to total some $67 million. This schematic shows the phases of modernization to date. The left box shows where the starting point was with a single contractor in yellow and various duties that the contractor had responsibility for. The next period was a period where HRSA was working to rebuild the OPTN. And during this period, there was not a lot of information coming out to the community. And there was a lot of angst and anger in the community because there was no information as to what was happening and where the progress was. But they did make a real concerted effort to improve the system with some 800 stakeholders that they surveyed to understand their opinions on what needed to be done to improve the system. And I recall a meeting that we had with a couple of other ASTS members with some of these surveyors. The surveyors looked like they were just out of college and took diligent notes, but how much they understood what they were writing down wasn't clear. So there was also internal and external expertise that was brought into the system to try to improve it. One of the most important steps was making the OPTN board independent. And that has been an important step forward and a real asset to the overall effort. In the beginning of this year, the full program was announced, and various contractors, probably 8 or 10 of them, will be involved, taking over for what UNOS previously handled. So this is a big step forward for the system, even though everything is not fully in place yet. It's all moving in the right direction. Another event that happened recently that caused some disruption in the field was the decertification of an OPO in Florida. Apparently, this OPO had long-standing performance problems. And in the end, the act was hailed as a positive event, having HRSA step in and take care of a problem that was long-standing in the system. Interestingly, an OPO in Nevada is overseeing that area of the country now, even though it's on the other side of the country. So there's a lot going on in the OPO field related to competition and the ability to take over other DSA areas. So this slide shows the oversight of the OPOs that are jointly overseen by CMS and HRSA. HRSA oversees the OPTN, as mentioned, that sets policies for distribution and ensures that the OPTN operates under NODA, and also works with CMS to monitor OPO performance. So CMS is responsible for certifying and overseeing OPOs as part of conditions of participation and conditions of coverage. And OPOs must meet specific performance standards to maintain their CMS certification and donation service area assignment. CMS also ranks OPOs in performance tiers based on donor and transplant outcomes. So what is coming soon is another potential area of disruption to the field, with a plan to make the OPO landscape competitive, where poor performing OPOs can be taken over by more successful OPOs. So there are 3 tiers of OPOs right now. The top tier is the top 25%. It has a top threshold rate for donation and transplant rates. The competition process allows these OPOs to compete for Tier 2 and Tier 3 DSAs. The Tier 2 OPOs that are above the median but not in Tier 1 are open for DSA competition, and they can compete for their own DSA and for other Tier 2 and 3 DSAs. And finally, the Tier 3 OPOs have rates below the median threshold, and the competition process for them does not allow them to compete because of this decertification. So how this is all going to play out isn't clear. It's not clear how a well-performing OPO or why a well-performing OPO would overtake a OPO that's poor performing. It would seem to only lower their transplant and donation rate. So there's a lack of clarity as to what's going on right now. So this shows the performance tiers for 2023 and the 3 levels of tier 1, tier 2, and tier 3. You can see there's a green band across the country. It's not clear why it ended up in that way. And a number of areas of red, they're poor performing and again, subject to being taken over. This was the change in 2024 with more areas that were in the 3rd tier and actually more areas also in the 2nd tier. There was an analysis done looking at the DSAs with greater than 9 million population. And you can see in this map, only one high-performing DSA was present. So it seems like a big mess. It's not clear how that's going to play out, but it too is adding more concern in the system, not knowing how it's going to work. As you've also probably seen, there's been a lot of bad press for transplant, including surgical teams that were about to harvest a man's organs until his doctor intervened, organ transplant network oversight that stalled due to the shutdown, a push for more organs is putting donors at risk, and the US donation system is facing scrutiny and changes. The key, though, is that trust in the system must be maintained, and right now, the trust in the system is somewhat shaky. This is another recent headline that organ transplant system is in chaos and waiting lists are being ignored. And this is a reference to allocation out of sequence. So if a kidney comes in that's from an elder person and the kidney is likely to have poor function and it's not clear which centers would want them, instead of following through the list center by center, they sometimes allocate it to an aggressive center to make sure the kidney gets used. But there's been an outcry from patients and others that skipping patients on the list is ethically incorrect. And this is an issue that has still not been resolved as how best to make this work. So around the time when there was trouble with some of these headlines in the New York Times, that we saw a 550% increase in donor registration removals from the National Donor Registry. And then on the bottom, you see that of 26 state registries, the data showed a 1,850% increase in donor registration removals from the prior week after the New York Times and RFK information was published. So again, trust in the system has been shaky, and there's a lot of work being done trying to address that. The other hit that the system has taken is the fall in number of opioid overdose deaths. That's obviously a very positive event, and opioid deaths were cut almost by 50%. But it also impacts the donor pool, as many of those opioid deaths provided excellent organs. So despite all these troubles, the system is still working quite well, and some 49,000 organs were transplanted last year. So I want to switch directions a bit now to a more positive side of the equation to discuss what is mentioned in this NEJM article from 2004. This was an article written by Sir Peter Morris, who was one of the real leaders in the early field. And what he said was, I'd venture to suggest that the next 50 years will be even more exciting, and we'll see the translation of laboratory models of tolerance to the clinic, the successful development of xenotransplantation, and the use of stem cell technologies for transplantation. And so those are the areas I'd like to comment on in greater detail. This graph shows the deceased and live donor transplant rates per million population for a diverse array of countries. As you can see with the orange bars on the right, which are the deceased donor transplants, the US is a clear leader, with Spain a close second. Spain was an early adopter of DCD and has also had an opt-in policy and strong cultural support for donation. On the left side, we see that the US is third in live donor donation, behind both the Israel and the Netherlands, which have significantly higher rates of donation. So stagnation in live donor donation is noteworthy, as we'll see in future slides. I think without question, the most important advance in the transplant field in some 20 years is the advent of organ machine preservation, making more organs available, including both DCD and DBD organs. We were fortunate while up at Mass General to perform the first warm perfused liver transplant in the US in 2016 when the trial just started, and the power of the approach was immediately evident. The paradigm is still evolving with NRP, normothermic perfusion, cold perfusion, and combinations thereof. For many cases, the technology is also performed permitting liver trans in the morning instead of the middle of the night. And this is important because it attracts young potential talent to our field, whereas being up all night had been a prior deterrent. So this graph shows the uptake in DCD organs over time. The orange line with the first arrow, there were approximately 500 DCD liver transplants a year, starting around 2016 when the trial first started. And you can see during the trial period up to 2021, there was relatively slow uptake, principally because of the regulations in the trial, or constraints in the trial regulations. When there was commercial use available in 2021, you can see there was a dramatic rise in use of DCD organs because of the availability of these perfusion devices. And this led dramatically to the organ pool. My estimate was there were some 6,000 DCDs used in that 4-year period that previously would not have been available. And so if you look at the top black line, which is all DCD and non-DCD, these added organs were responsible for this marked uptick in utilization. The new world of recovery surgery, a byproduct of machine perfusion, has also been a development for a novel career path for transplant surgeons as recovery surgeons, working from institutions or directly from third parties. At ASTS, we're following this closely to ensure that the field, as the field expands, that there's appropriate oversight to ensure quality and safety, especially if individuals did not complete their fellowship through ASTS. AST is also planning to offer additional credentialing for those non-ASTS fellows. Okay, I'm going to change gears a bit now and talk a little bit about stem cells and bioengineering. This shows a projection of cell and gene therapy market over the next 15 years or so. Probably the most powerful application to date of stem cells is the generation of islets for transplant, as this could potentially treat and cure a common medical illness such as type 1 diabetes, for which there are some 2 million candidates in the US alone. So this work was done by Vertex, here shown from the New England Journal, and it was championed by a famous Harvard scientist, Doug Melton, who, as the story goes, was a frog embryologist who recognized the potential for application in diabetes. He became motivated in part because he had 2 young children with type 1 diabetes. And their names were Sam and Emma. And so Doug started a company called SEMA, which Vertex paid just shy of $1 billion for the technology. And Vertex remains a leader in this field. While at Mass General, we were also fortunate to perform the first successful transplant with these same Vertex stem cells. This first patient was in desperate need. He had glucoses that would swing wildly and were unable to be controlled. And in one hypoglycemic episode, had a motorcycle accident that almost killed him and left him with a severe head trauma. He understood the potential risks and said that if he died from the procedure, he would be fine with it if it helped other diabetics in his situation. And I think this captures how desperate such patients are in need of help. Fortunately, the transplant was successful and his diabetes was fully reversed with half of the target dose and remained insulin independent for more than 3 years, ultimately succumbed to the brain injury he had suffered in the accident prior to transplant. But I believe his bravery and success in being the first patient really helped to move the field forward. So this shows the generation of islets from stem cells. It's been said that the ability to develop these stem cells through 6 to 7 stages can produce what look like normal human islets. Each step requires the right trigger at the right time to move to the next stage. And in this example, there were some 20 factors delivered with precise timing and dose through stages 6 and 7 to differentiate cells over a period of approximately 5 weeks. The stem cell-derived islets carry many advantages over the islets we used to recover from deceased donors. The advantages these cells carry compared to deceased donors include, and most importantly, a limitless supply for transplantation. The allogeneic islet preps we used to transplant from deceased donors carried about 70% impurities with exocrine cells, and only 30% were endocrine cells. And in general, it took processing 4 pancreases to get enough islets to reverse diabetes in 1 patient. Other advantages include that the immune cells are absent from the islets, yielding a pure endocrine population. So no macrophages, dendritic cells, or endothelial cells that could facilitate rejection. And the viability is upwards of 95%. Traditionally, these cells have been transplanted into the liver, as was done with islets from deceased donors, but now many teams are experimenting with different sites that would be more accessible. Like allogeneic islets, of course, these cells are foreign and immunosuppression is required. This shows the results of that first trial with 12 patients. The patients to enroll in the trial had to have severe hypoglycemic events that were uncontrollable and put them at risk of death from a hypoglycemic event. And they had to begin with an A1C greater than 7. And you can see that each of these patients over time, their A1C fell into a near normal range of between 6 and 7 or so. I think this is not a totally normal A1C, but the patients are also on immunosuppression that may account for why it has not dropped lower. The other interesting finding with transplantation of these cells that it took many months for the cells to gain full function. You can see here of the 12 patients that were transplanted, all 10 of them reached elimination of insulin somewhere between month 5 and 9 of their treatment, and all that became insulin independent have remained insulin independent. This shows another way to look at their data. This shows the time and range in the target range of 70 to 180 milligrams per deciliter, and you can see over time that increases back to what seems a perfectly normal level of 95% time and range. On the first bar at the bottom, there's a red bar that shows hypoglycemic episodes, and these too were eliminated over time with the transplantation of these cells. So a major step forward. So the Vertex work provides the first step and demonstration that cells function well and that a limitless supply is available. And importantly, to date, there's been no concern for development of teratomas that was a major concern when these projects first started. So the next objective is to eliminate the need for immunosuppression. This might be addressed in a number of ways. First is some very interesting work from a team in China that explores the use of autologous stem cell-derived islet cells. So this team used a protocol in which the stem cells are recovered from adipose tissue. The adipose stem cells are dedifferentiated and then redifferentiated into islets. This product is manufactured for a single patient with type 1 diabetes, so the cells should not be vulnerable to allogeneic rejection. The Chinese team that devised this used a different differentiation protocol and called the cells chemically induced pluripotent stem cells. And these are autologous to the patient. The only glitch is that we know autoimmune diabetes can recur post-transplant, even if rejection doesn't, and that could destroy the islets. So for these patients, they were not removed from immunosuppression. These patients had already had a liver transplant or another transplant that required immunosuppression, but the islets functioned well and provided proof of principle that this autologous approach could work. Now, it seems unlikely that the autologous approach will be something rapidly adopted because the process to make these cells for a single individual is really quite extraordinary. So the data I've just shown suggests that the supply problem posed by allogeneic deceased donor islets can become with stem cells. And my impression is that the reliance on autologous cells does not solve the problem of potential immune or autoimmune rejection. So the second problem to be overcome is to eliminate the need for immunosuppression. And for the first time, an approach was reported in the New England Journal a few months ago to address this issue. This was accomplished here for the first time in humans by genetic modification of the stem cell islets prior to transplant. And this group that reported this had previously done a similar experiment in a non-human primate that was very successful. So in brief, the team reporting this work indicated that they were inspired by a fetal immunity, recognizing the key targets of innate and adaptive immune responses. So specifically, they knocked out class 1 and class 2 molecules on the cells, on the stem cells, with the goal to avoid the adaptive immune response. But also critical to success was addition of a molecule called CD47 that is key in the innate arm of the immune system, delivering a don't eat me signal. In this preliminary work, the isolated islets came from a deceased donor, human pancreas. They dissociated the islets into single cells and then sequentially genetically modified them to eliminate class 1 and class 2 to add CD47. Of interest was that not all the modified cells carried the 3 edits, and the cells missing those edits were lost over time, but those carrying all 3 edits persisted, suggesting that the approach was successful from an immunologic perspective. I think, though a single case, the results are quite compelling, and we look forward to more follow-up in more cases. Obviously, the next step would be to advance this work to using stem cells instead of a deceased donor islets for proof of concept. Okay, I will change direction again. So I'd like to talk about live donor transplantation and the potential for deceased donor transplants and incentives to encourage donation. So this again shows the living and deceased organ donor growth over time. So the orange line is live donor kidney transplants, and the dark line is deceased donor transplants. And you can see that the live donor transplantation of the kidney has been essentially stagnant for more than 25 years. The reason for that is not entirely clear. On the bottom, we have deceased donor and DCD donor, and here you can see the dramatic rise in DCD in the orange line. So the issue of incentives to encourage donation of organs has been one that's been around for a long time. This paper from, I think 15 years ago from ASTS and AST looked at these issues and thought that the first priority should be to eliminate disincentives to donation, costs of medical care, being out of work, insurance, et cetera. And that has actually been very successful through ASTS and AST and other organizations. And that provides, it probably doesn't fully cover the burden, but it allows some significant compensation to cover those issues that they experience from donation. So this again shows the issue of live donation in yellow. For 20 plus years, there's essentially been no growth. And we have to balance that with the fact that some 5,000 people die on the list each year from either being too sick or dying from their disease. And over the last 30 years, perhaps some over 100,000 patients have died unnecessarily because of the lack of organs. So how can this issue be addressed fairly and ethically without exploitation and the concerns that have been had in the past? So the ASTS and AST are conducting a survey right now of both the general public and both the ASTS and AST members to gain further knowledge about their opinions of this issue. I also thought maybe Dr. Starzl's thoughts on it would be welcome as well.
I'll tell you what my position has been all along. I think that the idea that when a scarce resource becomes available and is freely given by a family, by bereaved family members, when somebody is killed under the circumstances that generate good organs, that precious resource generates a business in which everybody down the line profits. That's really not the right word. That everyone down the line has to be paid in order for the whole enterprise to go forward. And it has always seemed to me not entirely logical to believe that the only persons that can derive some economic support from the process are the people that have suffered the most or have been the most virtuous or the most community-minded, namely the donor or donor family. So great empires have been built out here based on this resource, and the idea that you shouldn't allow some kind of a remuneration, even for paying the cost of a funeral as a reward for that generosity, it just seems to me to be preposterous.
So of course he was right. There was a huge business of transplant that I had never even considered. It's valued at about $5 billion in 2023 with expected growth through 2030. In addition, the global market is 7.4 billion. And the economic savings to be had if global rates of kidney transplants were achieved, it would be a $6 billion year benefit in society and some 63 billion in productivity. And the broader impact includes or doesn't include tissue recovery, which is an $18 billion business itself. So I think his comments on doing something for the family as a gift or a thank you for having someone donate organs is very powerful, and hopefully we'll ultimately be able to bring that kind of issue forward. The STS Living Donor Committee has also extensively looked at this. Of course, there's no right or wrong answer, but they touch on the things that are usually commented on, the risk of, the potential to enhance altruism. We compensate for blood and sperm donation and surrogate pregnancy, so why not living donation? Why not living donation? And current models of removing financial disincentives is not enough. So we have more work to do on this, but I think it's an incredibly important topic. And I received this slide a couple of days ago from a colleague who showed that maybe the opinion of the general public is changing. So this shows on the left the likelihood of donating an organ if a payment is made for their own organs, and on the right for family member organs. So maybe there has been some progress in this area. So I just have a couple minutes left, but I did want to touch on xenotransplantation as there's a lot going on, and I will probably skip through some things. But if one's ever been to a xenotransplant meeting, they almost invariably start with the comment, xenotransplantation is the future of transplantation and always will be. And so that skepticism still persists, but there certainly has been progress made. Not surprisingly, Starzl was one of the pioneers in early xenotransplant. The first xenotransplants were done in 2006 by Jaboulet, but I think Riemsma did some 13 pig kidney transplants with one surviving 9 months. And coincidentally, 9 months is what the longest surviving kidney has been in the recent series. And Starzl, while in Denver, did 6 patients with baboon kidneys that lasting out to 3 months. There were a couple of other interesting cases. One was the only pig liver that was ever transplanted until recently. That was done by Leonard Makauka in a patient that had fulminant liver failure. He transplanted it as an auxiliary, and unfortunately, the patient expired. I think was probably too sick to have undergone the transplant. And then the last one of interest, of course, is Starzl's baboon transplant that lasted some 70 days with a pig liver. This shows a bit of the information around that transplant of a baboon. Sorry, it was a baboon liver, not a pig liver. So this was a baboon to transplant that he did. This shows the agents that were used to treat and prevent rejection. But I think what was probably of greatest interest was the rapid fall in uric acid and cholesterol in baboons. Compared to the human. And these potential incompatibilities could have impact depending on where in various processes they might be seen. And you can imagine with a pig organ, there's probably likelihood for many more of these incompatibilities that haven't been recognized yet. And I'll show you a couple of those in a moment. At this time, there was a lot of concern in the field. In the late 90s, and the main concern was of porcine endogenous retrovirus. There was a fear that this could turn into a pandemic, and this was on the heels of the AIDS epidemic. And this porcine endogenous retrovirus has never been found to infect humans, although human cells can be infected. But it did raise a lot of concern in the field as the xeno programs were taking off. Unfortunately, this was easily addressed with CRISPR technology. This line of pigs that the team from Harvard was working with had 59 copies of the PERV gene throughout the genome. And with a single treatment with CRISPR, they were able to inactivate all loci, essentially eliminating the concern that PERV could be a problem. So it probably never would have been a problem, but it's nice that it has reassured folks that it isn't a problem. Also of interest, the 2 main companies working in this area, Revivicor and eGenesis, somehow have come with essentially the same treatment regimens for their patients. On the left is the heart transplant that was done by Revivicor as T-cell depletion, B-cell depletion, anti-CD40 ligand, anti-CD40 interactions, tacrolimus, CellCept, prednisone, and a complement inhibitor. And you can see eGenesis uses almost essentially the same. All of these animals' organs had a triple knockout, getting rid of these carbohydrate antigens that cause the most trouble. For the heart, they included a growth hormone knockout so that the heart didn't undergo hypertrophy, as that had been seen in some of the animal experiments. And for the eGenesis, as mentioned, the PERV inactivation. The complement injury molecules for CD46 and DAF were the same in both the thrombomodulin EPCR for coagulation and inflammation were in both, as were CD47, HO1, with the only difference being A20. So how these 2 companies came with the same set of edits being essential is quite interesting. This shows the creation of the pigs for eGenesis. They undergo 3 stages of cloning. In the first one, they put in the triple knockout and put a landing pad in so they could insert the other edits. In the second round, they added those 9 key transgenes to deal with complement coagulation, et cetera. And then in the final round, they added the retroviral inactivation. And so the question was, do these edits really make a difference? And I think you can see very clearly now, without the 7 transgenes, the outcome is very poor, and with them, we get some prolonged survival. I mentioned the physiologic incompatibilities with the low cholesterol in the baboon, and we do see some incompatibilities in the animal models as well. There was some concern that the hearts might grow too large, but at least with these, that the kidneys might grow too large, but at least in these 17 animals that were studied, there was not excessive growth. There were some abnormalities in plasma renin activity and aldosterone. You can see the pre-transplant in orange and the post-transplant of the kidney. Thereafter, the levels are extraordinarily low in both aldosterone and plasma renin. So there's some incompatibility of sorts in this area. There was also calcium and phosphorus changes. You can see on the upper left, the starting level of calcium was somewhere in the 7 range, and it rose to nearly 12 and maintained that without any obvious problems for the animal. And the same, the phosphorus was exceptionally low. So with these, I'm sorry, there was one additional one, and that was parathyroid hormone was almost undetectable post-transplant with the new kidney. So these physiologic incompatibilities may be, again, more complicated and difficult to deal with, especially across broader ranges of species. So I know time is short, but I did want to talk about what's going on with the kidneys that have been transplanted recently. So to date, there have been 8 pig kidneys transplanted into human recipients. And these are live recipients, not the decedent model. The first patient was transplanted at Mass General back in 2024, and he died post-op at 2 months, and it was thought to be a cardiac issue, although it wasn't really clear from the pathology. And he did have an early rejection episode as well. The second patient, Tim Andrews, had a kidney transplanted, and it survived for 271 days, had a bad antibody-mediated rejection episode, and the kidney was removed, and the patient was fine. The third one is the longest to date. It was explanted at 8 months, again, because of a bad rejection episode. The MGH has another kidney that was transplanted some 4 months ago. It did have an early rejection that recovered, but is now doing well. The NYU team is the only other team that has really ventured into this so far. The first patient they did was a very interesting story. The patient needed a VAD, but you can't have a VAD without renal function. So Bob Montgomery put in one of the kidney thymus grafts that they use, so the patient had renal function. And the graft survived for 2 to 3 months, and the patient ultimately passed in hospice. And the second patient they did had a graft that survived for 4 months and 9 days, and it too was lost due to rejection. So it's sort of a mixed experience here. NYU has 2 other grafts going now that appear to be working well, but they're not that far out. So again, the longest survival is 271 days. It's a start. And the patient, while they have a pig kidney, it doesn't count against their time on the waiting list. So that helps a bit. In the last 2 minutes, I wanted to mention liver xenotransplant studies. Interestingly, these were done first in China. This was an interesting model where they transplanted a pig liver to the infrarenal cava inflow from the infrarenal cava to the graft portal vein. And it lasted for about 10 days. It had a series of modifications that are a little different than the ones that have been done in the US. But you can see here the graft when it was explanted, it didn't look too healthy. The second one of these that was done was an interesting case where a patient had a large hepatoma in the right lobe. They resected the hepatoma, but because the left lateral segment was so small, they put in a pig liver as a support so that the left lateral segment could grow. You can see the picture here with the portal vein anastomosis and recovery of perfusion once they restored flow. But over time, there was evidence of thrombosis in the graft. And you can see probably the most important factor was this consumption of platelets. If you look at the bottom box with the green line, the platelets start at 300,000, and within 20 minutes or so, they fall to somewhere around 20,000. And it's likely that this incompatibility of platelets with the human platelets with the pig liver is another one of these barriers that we're going to have to overcome. What the team at Penn is working on now, specifically Avi Shaked, has been trying to use an extracorporeal cross-circulation device to support patients in liver failure. And 4 of these were done with decedents. The first 3 were done over a period of a few days with the circuit active. And in the last one, the circuit was continued, but the native liver was removed to see how the patient would do. This again here shows the dramatic fall in platelets, both in the decedent model and the human non-human primate model. This is the setup with the liver. This is on an organox pump, liver being perfused through the decedent and followed over a period of 4 or 5 days. This shows the individuals that were involved. The one that had the native liver removed was followed for 2 extra days with the native liver out, and reportedly the decedent remains stable. This shows the perfusion while active. This is some histology, does show look like some red cell extravasation in the portal triad here. And so this is leading to a trial, both a pilot compassionate use trial and an FDA phase 1 clinical study to see whether liver perfusion on the pump could help sustain some of the patients in liver failure. And this is the trial that eGenesis is starting. So I know I've told you too much already, but I appreciate your attention, and it's been great to be with you, and thank you.
James, an amazing and efficient summary of what's going on in transplantation. Some of our I think we have a couple minutes for questions.
All right, thanks for coming to visit us. That was an incredible amount of information in such a short period of time. I want to go back to your part about the tiering of different organizations across the country and ask about the metrics that are involved in tiering, because whenever you choose metrics, it's going to determine the outcome or the final effect. And the one metric you spoke about was volume. And does focusing so much on volume, does that cause a secondary side effect that may be unwanted and perverse the system?
At least for the OPO discussion, volume was not one of the key metrics. It was transplant rate, and I'm blanking on the other, but there were 2 metrics that they used to tier the OPOs.
Do any of those metrics cause secondary side effects that you may not want to see?
So I think the metrics are being challenged by various centers. First of all, they change with time. And for some of the metrics like organ recovery rates, that's key for the OPOs. The OPOs are pushed to recover organs, many of them that are not going to be used. So the transplant rate goes down and it causes other issues. So I think there's a big push by the OPOs to try to address that with CMS, but it hasn't been taken care of yet.
Thank you. Any other questions? Dr. Yang.
Thank you. That was a great talk. My question is, you know, there's, I love your overview of all the new technologies and the new, breakthroughs being introduced into the field of transplant. One thing that I've been thinking about is there's so many different players that are involved in the decision making about, okay, well, what technology are we going to use? I'm talking about like deceased donors. And okay, so what pathway does this follow? In your mind, is there a way to consolidate this decision making, or the putting the key stakeholders in the driver's seat of this, or is this? Do you think that the decentralization, with all the, I guess, more of a corporate-driven change in practice, which way do you see the field going?
Yeah, great question. So the field is still really young, and I think that's part of it. Everybody wants to use their own device and own approach to it. So there hasn't been a consensus conference that says we should use this device and this perfusion approach based on these characteristics of the donor even. So it is pretty, isolated, where again, one hospital will want to use Transmatics, the other will want to use Organox, and they're not talking to each other. So I think right now, at least, it's hard to see these things coming together to a cohesive, we could do it better if we all work together, but that would be the ideal.
Liver call certainly has changed. If you're looking at a donor, you have to understand what technology the thoracic team is going to use. That changes your decision on what potential recovery method we're going to use. So the logistics of recovering organs has just significantly changed over the last several years. And the amount of work done needed to recover an organ, bring it back to your center and transplant it, just from the logistical side, has significantly changed. Well, James, thanks for being our SWAN professor. We have a bag here full of swag. Most notably now, you can sport a University of Colorado tie when you're rolling around the University of Pennsylvania and represent us.
I was admiring them earlier this morning.
Thank you very much.
Thank you.